Okay, we will quickly run through the neural network fundamentals for ASR. So to begin with, we will start with the neural networks themselves. There are certain references that I found useful and your earlier teachers have already used them and taught them. There are NPTEL courses on those, and we have gone through the introduction to neural networks, the gradient descent algorithm for training a simple neuron, or this algorithm is useful for any kind of optimization. Machine learning is a popular machine learning algorithm, and the algorithm applied to a multi-layer neural network, the algorithm is called backpropagation algorithm. We will quickly run through each of these. This is a schematic of the human neuron inside the human brain. A neuron takes inputs from thousands of other neurons, does some computation inside the nucleus of the neuron, and then once in a while it decides to send some impulse out of the neuron, which gets connected to other neurons and so on. So the primary function of a human neuron looks like take input, do some computation and give output once in a while. In an imitation of the human neuron, when we build a neuron, it is called an artificial neuron. It also tries to do similar job. So the mathematical approximation of the human neuron is that there are some inputs, let's say x1, x2, x3, let's say there are 3 inputs. You make a linear combination of these inputs, which means that you multiply x1 by a number, real number, which could be positive or negative, which you call it as a weight. And so in the past, if the neuron has seen that any input coming from this neuron, if it is positive, this output also should be positive. They work in synchrony. Therefore, the W1 corresponding to input from the another neuron x1 will be positive. On the other hand, it has also found that whenever the new input comes from second neuron, if the input is positive, the output of this is negative. Therefore, it assigns a weight which is negative. W2 could be negative, and so on. So for each of the inputs is multiplied by a weight and they are added. This can also be seen as summation of Wi xi, I summation over the I. In this square there are 3 inputs. This output can also be thought of as a y. Input vector is 3-dimensional vector. There is a 3-dimensional weight vector. The dot product of the x vector and the weight vector it gives rise to a scalar, which is y, the output. That y, if the y is greater than some threshold, let's say theta, then the system will send an output. Otherwise, the output would be 0. Otherwise, it sends 0. So, this is how the neuron works. This idea is mathematically transformed into a simple neuron, and that such a neuron was first postulated in 1969. Before that also, even before the World War II, there were some thoughts on this metalectric neuron, but we will not do it. So, this is called a perceptron. Whitetron, anything to do with the machine, electron, proton, neutron, neutron, something that is computing. It is related to the perception of patterns by the humans. That's why it's called perceptron. And so the perceptron could make a binary decision. or 0, true or false, yes or no, or class 1 or class 0. So in this particular case there are two features, x1 and x2, and in this two-dimensional feature space, two classes, the green class and the blue class, they seem to be separated by a straight line. This equation represents a straight line if the perceptron, which is also called a linear perceptron because it is a linear combination of the inputs, is able to do a classification, if you wish, depending upon this kind of boundary decision. It can also compute, without even this boundary decision, given an input x vector, it can compute the output y. So it can do a curve fitting, a regression, but it is a linear regression. So neuron can be used for feature mapping from the x vector to an output y, a straight line. Or in addition, if you also put this kind of decision function, this so-called activation function, it can do a binary classification. So this idea, whatever I wrote here as summation wixi, is shown here schematically in this graph. So in this particular graph, there are four features, x1, x2, x3, x4. Collectively, we call them as a feature vector x. Each of the feature is multiplied by the corresponding weight w. x1 is multiplied by w1 and added here to x2, w2. This is summation wxi, what I wrote here. That is computed and a decision function is made. Now this decision function is called activation function. So this f is so-called activation function. We talked of one type of function, which is if this weighted sum is greater than threshold, you send output y equal to 1, otherwise output y equal to 0, a binary decision. So this activation function is a kind of decision function. This is not the only activation function that we can think of. We will think of others too. But let us see, what are these weights? What should be these weights so that I get the desired output y when a given input is given. So this is the purpose of a neuron. Neuron should do the appropriate decision. What is appropriate decision? You give several examples of the input vector x and also tell what should be the desired output. You know the desired output of the class label 0 or 1 because these are the training data. So you tell the desired output of the target output y, and the weight should be adjusted, should be a such value that it makes the correct classification most of the time. So we take lots of training examples. Let's take a training example. Let's play x. And its desired output or the target output is t. The input is x of n, nth training example. Its desired or target output of the nth training example is t of n, which is 0 or 1. And if this neuron is initialized with some random weights, its weighted sum is computed and the activation function is applied, which is a thresholding in one particular case, the output is produced. So corresponding to an input x of n, we have an output y of n, and the target output, the desired output is t of n. The difference between them is the error. In this particular simple case, error could be 0 or 1 or 1 or minus 1. In case of a regression function, it would be any continuous real value. So this is the error. The error could be positive or negative, so we square the error. So the squared error, we sum it over all the training examples, and that is the cost function or the loss function. We want our error function. we want to minimize the total loss, total squared error. So this is a function of the weights which are here. Our goal is to adjust these weights so that these loss over all training exams, summation over all n, is minimized. Let us take one particular weight. There are several weights here, 4 weights here. Let's take one particular weight. How do you minimize this? Gradient descent algorithm says that the weight should be adjusted such that the change in weight should be negative of the derivative of the loss function with respect to w. That is, the new weight should be old weight minus the into derivative of the loss function with respect to the weight. Now you can do a partial derivation of the error function with respect to given one particular weight. Now, and this, if you compute from here, and y of n is nothing but summation of wi xi, assuming that this function is a linear function, then the new weight at the time new weight at the iteration number n plus 1 would be old weight minus the error into the input. The error is d is the same as t, desired output or the target output, minus the actual or computed output of the neuron into the input x of n. So this is the weight updation rule. This weight updation rule can be applied to all the weights here. So this algorithm guarantees that the weights change in such a manner that the error, total squared error becomes least or minimized. So this is the gradient descent algorithm in a nutshell as applied to updation of the weights of the neuron. I did talk about this activation function. In this, the activation function would be just linear, which means f of x would be just x, which is regression, case of regression. Now, on the other hand, you can do a decision if the f of x, this y is greater than a threshold, then 1, otherwise 0. So the f of x could be if y is greater than theta, then it is 1, otherwise 0. So this is a by thresholding function. This is a linear function, this is a thresholding function. Many times we need something different than that. What is that we need? We may do a classification just into 2 classes, but we do not just want the decision whether this is belongs to class 1 or class 2, but we may also need a confidence with which we classify the given input to class 1 or class 2. So when you talk about confidence level, the simplest one comes to my mind is probability. So what we want is the probability of the x vector belonging to class 1. This is what I want. So if the probability of x belongs to class 1 is, let's say, 0.7, what is the probability that it belongs to class 0? It will be 1 minus 0.7, 0.3. So if you can find out this, I know the probability for the other class also because I am doing a binary classification. So the probabilities are numbers between 0 and 1. On the other hand, the weighted sum can be a number which could be from minus infinity to plus infinity. So we need an activation function which will transform from with this y, which could be in the range minus infinity to plus infinity, to a range between 0 and 1. There are several such functions. One of them is called sigmoid function. A logistic function is given here. Its expression is 1 over 1 plus e power minus x, and this ensures that whatever will be the input minus infinity to plus infinity x, the output will be between 0 and 1. This is useful when we use probabilistic models. There are other similar functions. One is called time hyperbolic, whose output is between -1 and +1. And there are a few others. We will talk about it as we move along. And something that you see here is the name of the such activation functions are here. Their curve of the activation function is given. The equation of the activation function is given. You also see that the derivative of the activation function is also given. And you will see that the derivative of the activation function is necessary when you update the weights or during the training. That's why this is given. Okay, now we will move on to the little more mathematical details of training a neuron. First we will train a single neuron, then we move towards the multi-layer perceptron or multiple neurons in a layer and multiple layers of the neurons. We are going to use the logistic regression function as the activation. This function, which is given by f of x, is equal to 1 over 1 plus e power minus x. X could vary from minus infinity to plus infinity, output will always be between 0 and 1. Logistic regression. In this particular example, he has taken one neuron. He has considered one neuron, single neuron. There are three inputs, x1, x2, x3. There are corresponding weights w1, w2, w3. The weights are associated with the arc between this node and the neuron. So the summation WAXI is here. There is also a bias which is quite often used in the thresholding. So the bias is kept here. So the bias, the input to this bias arc is always taken as +1 and the B is treated similar to the weight. That is, B is also adjusted. So this is summation WAXI into B. Sometimes some of the textbooks consider this as W0, a weight, 0th weight itself, and this as x0. So this summation can be written as WIXI, I starting from 0 to 3. 0 belongs to this. Why do you do this? Because this can be treated as the dot product of input vector x and a weight vector w. That is the reason. So whether it is in MATLAB, it becomes much simpler. When you write a C or a Java program, it becomes easier to implement. But some people explicitly write a bias. We should get used to both of them. As you see, the vector W, which I wrote here, is a three-dimensional vector. Three-dimensional vector can also be written as a column vector, column matrix with the three rows, W1, W2, W3, W0 also if you wish, and one column. Okay, so it's a matrix of 3 rows and 1 column. All these 3 inputs feed to one neuron. So this collection of these inputs is called an input layer. Graphically they are denoted one below the other. Why they are called as one belong to one layer? Not because it is arranged graphically here, but because all of them feed into the same neuron. This is one neuron. There is a problem with, there is a limitation of the single neuron. Single neuron can place only one linear boundary, but if our classes are multiple mutually exclusive regions, such as in the case of the XOR problem, then we need more than one neuron. What we will do is, the same set of inputs also feed into another neuron. This is, let's say, neuron 1 and this is neuron 2. So these x1, x2, x3 and that would feed into the another neuron 2. So since all these inputs feed into 2 neurons, These two neurons are said to belong to a single layer. This layer is called output layer. Why it is called output layer? This may tell the probability of the input data belonging to OL class. This may tell the probability that it belongs to constant class or some other class. Input data can be merged several classes, in which case there will be several neurons in the output layer. Each neuron tells the probability, posterior probability of the input data belonging to each of the classes. So, we are now talking about a layer which is input layer and a layer of neurons which is output layer. Now we are talking of, in some sense, two layers, but the input layer does not do any calculation. It is only the output layer, the layer of neurons, which does all the calculations. This has limitation. The limitation is that this cannot handle a class which has two mutually exclusive areas. The standard example is XOR. Therefore, we go beyond this. We will have not just one layer of neurons, but multiple layers of neurons.